Most of us have seen meteor showers, bright streaks of light in the sky, but what may not have been apparent is that these meteors can be used to transmit messages from one location to another. This technique, known as meteor burst communications, or MBC for short, in its current form takes advantage of a long history of research that touches on theoretical aspects of meteor, atmosphere, and radio theory.
The clock has to be turned back a few centuries to gain a view of the principles of the atmospheric interaction in meteors, on which our modern understanding is grounded. The German astronomer Ernst Chladni first proposed the theory that, quote, space is filled with flying particles which are ignited when they encounter the Earth's upper atmosphere. Chladni's theory sparked a brief period of scientific interest in meteors, which led to the rough calculation of the height at which meteors enter our atmosphere. It wasn't until later that it was recognized that the igniting of those meteors caused a peculiar phenomenon named ionization to occur. The earliest relation posited of the possible relation between meteor trails and radio waves was introduced in 1929 by the Japanese scientist Nagaoka. Nagaoka's initial understanding was that the trails, quote, swept away ionization rather than facilitating it. Though incorrect, Nagaoka's early investigations laid the groundwork for further research that led to the correct understanding of the meteor trails as a medium particularly suitable, practically exploitable even, for the propagation of radio waves, commonly referred to as the forward scatter technique. The post-World War II period saw a dramatic increase, because of its usefulness during the war, in the use of radio technology for practical applications. One area where this can be seen is in meteor burst communications, where government-sponsored systems were set up, first in Canada with the JANET system, and also in America with the mid-70s SNOTEL system. Research in MBC in the late 80s to mid-90s was expanded mainly due to interest from the military, where MBC, because of its operational simplicity and survivability in adverse conditions such as solar flares and nuclear scenarios, was seen as valuable. Contemporary research in MBC is, in the main, concentrated on efficiency and data rate improvements, and, in the case of the SNOTEL system, still in use for collecting meteorological data for the western United States.
Meteors igniting due to friction from entering the atmosphere creates ionized particles that can be used to reflect radio waves. A remote transmitter sends a signal that is reflected from the ionosphere. This means that as opposed to a system of radio towers, one control center can send or receive messages to or from any location within a 2,000 kilometer radius. The stability of the ionized particles is an important factor when transmitting and receiving data. The ionized particles leave a trail that can be classified in two ways, namely underdense and overdense. Having an overdense trail can increase the time frame of communication. Underdense trails, on the other hand, cause lag time between transmission, but occurs frequently. Since meteors are a major factor in MBC systems, things that affect meteors can in turn also affect MBC. Earth's gravitational pull is essential to ensure there are sufficient numbers of meteors for transmission. As the Earth continues to spin around the Sun, the part closest to the Sun attracts any meteors with its gravitational pull. In any other areas, meteors with orbital speeds higher than Earth's are essential for transmitting messages with MBC systems. Due to these factors, the best time to use MBC is in the morning when the sun rises.
Discussing the applications of a technology can be approached in two ways. We could mention the future applications, or we could talk about current instances of its application. Meteor burst communication invites investigations into both of these. In terms of theoretical use, MBC can be used in all the capacities of traditional long-range communication technology, albeit with low data rates. The system, because of its low power consumption and reliability, can be used in remote places where systems that are more susceptible to atmospheric conditions, like satellite communications, would be impaired. One proposed application for MBC is for it to be used as a communication system in case of a planetary exploration mission on Mars. The main requirement for MBC, sufficient meteor trails for reflecting communication signals, exists on Mars just as it does on Earth. Of applications that are in use today, One could mention the snowtail system, used in the western United States to relay meteorological data such as temperature, wind velocity, as well as snow and precipitation data. Another positive aspect of MBC is reliability, a characteristic that is highly valued in military equipment and operations. Traditional communications mediums suffer the possibility of being disabled in adverse conditions such as solar flares and nuclear scenarios. MBC, because it does not rely on the atmosphere, but rather the continuously generated streams of ionized trails left by meteors, continues to operate in these adverse conditions, and therefore provides a vital backup communication system. Meteor burst communications is an old technology, which has found its niche in the world, and it appears will continue to fill that niche long into the future.